Hello, and in this video we're going to talk about the concept of probability mass functions. Some people call it a PMF, and we're going to exemplify it with three different examples. So let us first define what a probability mass function is. So definition. So let x be a discrete random variable. If the variable x is a continuous random variable, that will be what we call a probability density function that is going to be associated to it. So if this is true, then the function p, which will map an event from some sample space to the interval 0 to 1, of course a subset of the reals, is a probability mass function. If the following properties are satisfied. The first property is that this function p of x is always between 0 and 1. And the second, the sum of all the probability values is going to be equal to 1. And this is for all values x. So let us give a particular example. So flip two coins. So if we flip two coins, we already know the sample space that's associated with that, right? Namely heads, 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 tails, tails, heads, and tails, tails. Namely, the size of the sample space is going to be equal to 4. And I'm going to define x be equal to the random variable associated with the number of heads. So if x is associated with the number of heads, then what are all the possible values that x can have? Well, you can have 0 heads, 1 heads, or 2 heads at most. So what is the probability of obtaining 0 heads? Well, that's only concerned with one possible event, so that's going to be 1 divided by 4. What is the probability of getting 1 head? Well, that's going to be associated with HT and TH, so that's going to be 2 out of 4. And what's the probability of getting 2 heads? Well, that's just associated with HH, so that's going to be 1 out of 4. So notice that all of these values here, all of them are bigger than or equal to 0. So that property is clearly satisfied. And 1/4 plus 2/4 plus 1/4 is equal to 1 as well. So that's the first property of probability mass functions, and that's the second property. So therefore, this is the probability mass function table. And of course, since it's a function, you should be able to generate a graph for it. So let the horizontal axis be x and let the vertical be p of x. So our values are going to be 0, 1, and 2. And we have 1/4, 2/4, and 1/4. So our values are here, here, and here. So it's almost like a frequency distribution, except that the vertical axis is probability, not frequency. And if we were to connect this, then this would pretty much make like a little triangular shaped region, right? So that's going to be the probability mass function for the random variable of obtaining heads if you flip two coins. So let's do another example. So example 2. So let's roll 2 dice. So if we roll 2 dice, then that means the size of our sample space is going to be equal to 6 squared, as before. And we're going to let y represent the random variable of the sum of the die. So what are all the possible values associated with y? So y can range from 2. This is coming from the event 1, 1. You could get 3. This is going to give us 1, 2, 2, 3. 4 is coming from 1, 3 2, 2, and 3, 1. All the way down to, let's go to 7. So how can you get 7? Well, 7 is going to come from 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. After 7, that's going to go to 8. So can you get 8? So 8 is going to come from, let's see, 2 and 6, 3 and 5, 4 and 4, 5 and 3, and 6 and 2. And then it's going to go from 9 all the way down to 12, where 12 is associated with 6 and 6. So what is the probability of this value y? So the probability of getting to 2, well, there's only one event associated with that, so that's going to be 1 out of 36. 3 is going to be 2 out of 36. 4 is going to be 3 out of 36. And this is going to increment by a 36th every single time until we get to 7. Now 7 is going to have the most values, right? Namely, we have 1, 2, 3, 4, 5, and 6 out of 36 values. 8 is going to have one less, namely 5 out of 36, as we see here. And then it's going to drop all the way down to 1 out of 36 again. So this is the probability mass function table for y. So if we graph this value, so this is going to be x and this is p of x. So the least value is going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have 1 out of 36, 2 out of 36, 3 out of 36, 4, 5, and 6 out of 36. So if I plot all my values, then I'm going to have this type of behavior. So note that 6 over 36 is corresponding to 7. It's not exactly drawn to scale, of course. And then it's going to drop back down. So it makes this triangular shape again, of course. So of course, is this a probability mass function? If so, then those two properties will be satisfied, right? So notice that all these values are above the x-axis, so that property is no big deal. What about the sum of the probabilities? So property 2. So the sum of all of these values is going to be 1 out of 36 plus 2 out of 36 plus all the way out to 7 out of 36, then drop down 6 out of 36. No, the highest is 6. So 6 out of 36, 5 out of 36, all the way down to 1. So if we factor out a 1 out of 36, then this is just going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So this is going to be a little bit more easier to add. So that's going to be what? So that's going to be 3. That's going to be 3. We have a 3 there and a 3 there, so that's going to be 6. There's a 6 there. We have 5 plus 5, that's going to be 10. 4 plus 4 is going to be 8. And what do we have here? So we have 6 plus 6 plus 6, that's going to be 18. So we have 18 plus 10 plus 8 is going to be 18. That's 136 times 36, and then that's of course equal to 1. So therefore, this function serves as a probability mass function, and we verified that both of the properties definitely do satisfy. So let us do one other example. So let p of x be equal to 1 divided by 15x, and that's if x is equal to 0, 1, 2, 3, and 4. And let it be equal to 0 otherwise. So is this a probability mass function. So we can graph this to sort of see if it's always positive or always negative. So this is x and this is p of x. So when x is equal to 0, y is going to be equal to 0. When x is equal to 1, that's going to give us 1/15. When x is 2, that's going to give us 2/15. When x is 3, that's going to give us 3/15. And when x is equal to 4, that's going to give us 4/15. And this should go up to, I believe, 5, right? Yeah. And if that's 5, then that's going to be 5/15. So if we plot all our values, then we should get a discrete line. So it's always increasing, and definitely it's always positive, right? So always increasing. And how do I know it's always increasing? Well, the probability mass function is a linear function, and the slope is bigger than 0. The slope, which is 1/15, is bigger than 0, so it's always increasing. And the minimum value is 0, so that's always, bigger than or equal to 0. So no big deal there. So property 1 is p of x always bigger than or equal to 0? Yes, that property satisfies. 2, what about the sum of the probability values? So all the values of interest are highlighted in blue. So that's going to be 1/15 times 0 plus 1 plus 2 plus 3 plus 4 plus 5. So 0 plus 1 is 1, plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is going to be 15. So it's going to be 1/15 times 15, and that's, of course, equal to 1. So therefore what? Therefore, p of x equals 1/15 x for x is equal to 0, 1, 2, 3, 4, and 5, and 0 otherwise is a probability mass function. And that's pretty much a summary of probability mass functions. There are two very important properties that are going to be associated with this, which we'll discuss in the upcoming videos. But most of all, we're going to be focusing on particular types of PMFs that are really often occurring in nature and some particular scenarios. But that will be in the upcoming videos as well. But overall, that's a brief summary of probability mass functions.